Okay, so we're done with, I would say, more or less the simple stuff, okay, and in terms of the pre-processing steps. And we're going to move on to something that's a little bit more complicated now. And that's to do with, because up to this point, what we've done is we have taken care of each subject's motion, slice timing issues, and also the co-registration, um, co-registering each subject's high resolution structural images to each subject's high temporal resolution um, EPI functional images. Yeah. Uh, and up to this point, we've really been more or less concerned only with the subject in the subject's space. So you'll note that everything is still done within this subject's native brain image space. But very often in fMRI studies, where we collect many subjects, a group of subjects, we will want to have kind of like a common template where we can say, like, in this coordinate XYZ location, everyone's hippocampus is in this location. We want to bring everyone's hippocampus or different brain structures to the same template so that we can make meaningful group level comparisons and make meaningful group level statements about that location, about that same brain structure. All right, this is difficult because everyone's brains has different size and different shapes. It wasn't an issue when we were working with just the single subject. We could just apply rigid body transformations, XYZ translation and XYZ rotation. But when it comes to moving or deforming or reshaping a given subject's brain to a common template or a common map, that we can't use the rigid body assumption. All right, we have to do some sort of deformation, which means to change the shape of the image, to change the shape of the brain so that we can fit every different shapes of brains to a common brain shape. Right. So we talked about this in detail in class, right? So I'm not going to go through that again, but this is where we are moving on to in this tutorial. And the first step we're going to do here is we're going to apply segmentation here. All right, and that's this button here. A little note about what this does, and also contrasting this to another similar algorithm here. Actually, they do the same thing now. They didn't used to before in SPM, right? But now it's been set up so that the segment function also applies similar algorithms in SPM as the spatial normalized function. I won't talk about this here right now in this tutorial because I want to just go ahead and focus on the segment for now. We might come back to the normalized function in another tutorial. What segment will do is it will take your structural image and it will segment it into different kinds of masks. So we usually operate on the T1 image here. Okay, so what segment will do is it will take your T1 image. Remember, T1 has gray matter is gray, white matter is white, CFS is black. And it will segment that T1 image into several different kinds of images, and you'll see later it will have a gray matter mask, a white matter mask, CSF mask, and so on and so forth. All right, and it does this as a first step, and in addition, it will compute and derive some parameters that will be useful later on that we will be using to do the spatial normalization that I talked about, the deformation, where we will want to bring this subject's brain to a common brain space. In our case, the Montreal Neurological Institute, the MNI brain space. All right. So again, I will talk about this in detail in class, but here I'm just going to show you how to get that, how to use this tool here. And it's really very easy in terms of using it, but I really stress that you should spend time to understand what is going on here and not just go through the clicking motions, which I'm just demonstrating to you here on this tutorial. All right, so we want to segment the T1 images. The goal here is to work towards a spatial normalization of this subject to a MNI to the MN from the subject space to the MNI space. All right, so which involves several steps. And here first, we're going to do the segment step, which is the very first thing. We're going to split the T1 into gray matter, white matter, CSF images, and then also derive some normalization parameters, which will be used later on. And here, if you click on segment, the batch editor will open, and as you see the X's, it's very simple. You just need to fill it up. In this case, you can see select scans from this channel for pre-processing. If multiple channels are used, T1, T2, then the same order of subjects must be specified so that they match. In our case here, it's really very simple. We just want to perform the segment on the one subject's T1, Y01's T1 that we have co-registered. Remember, you must be very aware of the images, where they're co-registered, where they are in space, because the file names don't tell you. And if you don't do the right thing at the right time on the right file, then things will get messed up. All right. In this case, we've co-registered. You need to note that T1 has been co-registered to the T2, which was already co-registered to the EPI. So effectively, this T1 is co-registered to the EPI, and all the other EPI volumes were co-registered to the first EPI volume. All right. So in other words, the T1 is now co-registered to all the EPI volumes. And that's the one that we want to segment. So we're going to select that, just this one subject for now, Y01, T1, that's co-registered to the EPI. And that's pretty much it. There's really not much to do in terms of the setting up of anything, but there are certain settings. You can see there's no more X's we need to fill in, all right? But this is misleading because what we do need more information than the default of these settings. So here, at least for this tutorial, I'm just going to talk about these. We're going to skip these because this is to do with getting a bias field correction. We won't have that problem here in this data set, so I won't get distracted to talk about it. But we will have different tissues. These are, as I said, the gray matter, the white matter, the CSF, and several other tissues, up to 6 different kinds of tissues. So what SPM will do is it will segment the T1 into these different tissue probability maps, all right? And it will do it using some predetermined information that SPM already had. The researchers did many scans, and they have a tissue probability map that's located in your SPM TPM folder. If you're not sure, here, you can go navigate to it, to your SPM folder. That's what I'm going to do here, and I'll show you that if you go to the SPM 12 folder and go to the TPM location, which is right here, you'll see that there is a tpm.nifty. This is a template image that consists of the different tissues, gray matter, white matter, and CSF. And if you want, you can open it using MRI cron, and you'll be asked which volume you want to see. It's because this is a 4-dimensional image, and the first 3 dimensions are the typical XYZ dimension. The 4th dimension are the different tissues, whether it's the gray matter, white matter, CSF. All right. So I do encourage you in your spare time, go play around with this image, open it in MRI cron, and you'll see what I mean. But SPM will use TPM volume 1 to do this segmentation. And in this case, this is the gray matter. So the TPM first volume is the gray matter. And then it will ask you here, if you click on native tissue, the native space option allows you to produce a tissue class image C** that is in alignment with the original, so that it can also be used for importing into a form that can be used in the Dartel toolbox. And we'll come to that later which requires an RC asterisk kind of file. All right. Now the options are none. You don't want any native space image which has a C in front of it, and you'll go through that later. Or you want a Dartel imported one, or you want both, which is the RC image. We want both because we will be doing Dartel in this course. So make sure you select that for the gray matter. In this case, it will be it's a C asterisk. If it's a gray matter image, it will be labeled C1, and you'll see later the outputs that are given. Warp tissue. This is spatially normalized versions of the tissue class. So and you'll note that it says spatially normalized, which means that it will be normalized to a common template space. In this case, the MNI space. So segment will produce normalized tissue. All right. Technically, we don't really need this, but it's my habit to just collect everything and generate everything anyway. So we're gonna do modulated and unmodulated. The difference between modulated and unmodulated is kind of described here, and you can read it in detail. But the summary is that basically, if you change the shape of the image, then you gotta determine how do I account for the fact that the shape has changed. One way that SPM does it is, let's say you shrink the shape, then it might modulate the intensity that is in the shrunken shape, right? And that would mean that actually it's more dense. Okay, so we'll talk more about this in class, but for now, we're just gonna select both modulated and unmodulated. And this is for gray matter TPM volume 1 or frame 1, all right? But we're gonna go ahead and do it for all the frame 2, which is the white matter, frame 3, which is the CSF. So I'm just gonna go ahead and select native and Dartel for the white matter frame, modulated and unmodulated for the white matter frame, and so on and so forth for the CSF. And the fourth frame, I can't remember what it is. It's probably skull or something. But it's really not so important after frame 3 for the most part. The key ones are really the CSF and the white matter. It's also important to realize that why SPM is using this segment approach. It's because if you think about it, if you want to change the shape of the brain, really one of the most important parts, information, there's a lot of information in the T1, and really all you need is kind of like the cortical ribbon, the gray matter, right? That's kind of like the outline. And if you change the shape of the outline, well, you already fit the white matter part. You don't need to recompute anything, all right? And in fact, it simplifies the calculation a lot. So that this segment approach, this segment step, is one way to do the normalization using a deformation procedure where you change shapes. There are many ways to do this. This is just a way that it's adopted in SPM and also in some other programs as well. All right, so after you've set for TPM6 to produce the native and Dartel imported information and the modulated and unmodulated information, the other parameters at the bottom here, you can see that there's no x's, that they are by default. But we do want to take note that it does some affine regularization first, okay, so that it gets reasonable initial starting estimates. Again, we'll talk about this in class, but so it's like a starting point for SPM to do its work, right? And in this case, it uses the European brains ICBM space template, which is the MNI space brain, okay, but based on European brains as the starting point. In the case of this project, the data are European brains, so we're going to leave it as is. But in your case, if you are collecting data from more Taiwanese or East Asian people, then you might want to switch the template to the starting template to the East Asian brain or some other setting, all right? For now, we're just going to leave it as is. Everything else is the same. The only thing that's changing, that we want to change, is this one, which is the critical one, is the deformation fields. Go ahead and click on it and read the bottom. And here you'll see deformation fields can be saved to disk and used by the deformations utility. For spatially normalizing images to MNI space, that's what we want, you will need the forward deformation. Whereas for spatially normalizing all these other files, which means you want to go from MNI space back to subject space, you'll need the inverse. So we're going to do both. You can see here that right now it's none is selected. We're going to do the forward and we're going to do the inverse as well. All right. What this means is that it's going to generate, after this segment step, it's going to generate a parameter file which tells SPM how do you warp this subject's brain to reach the MNI space, that's the forward deformation field, and how do you warp it back from MNI space back to the subject space, that's the inverse warp. All right, so it will generate both these information. So that's all the setting we're going to do. We're going to save this. And I'm going to put it again in my subjects file. In this case, I'm going to call it segment. Save. And I'm going to run it. And the minute I run it, it's going to take a long while. So for that, I will skip ahead and come back when the segmentation of sequence analysis processing is done. So I'm just going to play, and it's going to do its thing. It's going to take a while, and I'll skip ahead and to the end. Okay, it looks like it's done. And I'm just going to look at the outputs, all right? So if we go to the subject folder again, you'll see now a whole bunch of stuff has been created. And starting from, I think the most important one for now are the you'll see that there's a C1, Y01, T1 image, C2, a C3, 4, 5, 6. These are the tissue probability maps, the segmented tissue probability maps derived from the original subject T1. So this is the subject's gray matter, white matter, CSF. And in addition, you'll see the IY T1, it's a nifty image, but this is the deformation field. This is the inverse deformation field, and you have the forward one, which will be labeled Y. So this is the forward deformation field that we want, and the inverse deformation field that we want. Now it's important to note that this C1 image is going to be in subject space, all right? But you will note also that there are these MWC1 images and also a WC1 images. Let me just highlight these 3 different images so you can see. So if we just focus on C1, C1 refers to the gray matter images, all right? And you can open it with MRI Cron to take a look. You'll see it's just a very nice gray matter mask, okay? And then the WC1 are these C1 images that are now normalized in MNI space. That's putting a W in front means that SPM has normalized it to some other space. So you've gone from the original subject space C1 to now an MNI space C1. This subject's C1 in MNI space. And then this is not modulated. Remember we talked about modulation, like if you change the shape, you're gonna, might you change the intensity to indicate some sort of a changes in density of the brain tissue, and that would be the modulated case here with the M in front. So this would be the unmodulated. So you only change shape, but you don't change the numbers. Okay, so you lose that information. But here you have the intensity is changed so that you preserve the shape as well as the original. You preserve the original shape information by converting it to densities. Okay, and then you also get the RC1, C2, C6. These we will use later on in the Dartel case. So this is the segmentation step. It's done. It took a while, but we're going to have to do this for all the subjects before we move on further in our pre-processing steps. So in the next tutorial, we'll be talking about batching all the pre-processing analyses that we've been doing so far.